Let us continue our discussion on applications of electronic systems and circuits. In the last class, we discussed about an application to a temperature control system which is widely used in process control industries. Let us now consider a very simple system, an electrical system in general and an electronic system in particular. That is a public address system. Please look at this figure. So this is a public address system. It uses a microphone. The microphone converts the sound signal, so the sound signal into an electrical voltage. So it becomes a voltage signal. Okay? Basically, it is a pressure as a function of time. It's a time function is converted to a voltage as a function of time, a voltage signal. Then this voltage signal usually is very small in amplitude. Then to rise the power level of this voltage signal, we use an amplifier, and the amplifier increases the voltage of the signal. Rather, it is amplified by a constant known as gain times, and the output signal is gain times the input signal. If the gain is 100, the output is 100 times the input signal. The shape remains the same except for a rise in the amplitude. That's what is an amplifier. And the amplified signal GVT is then applied to a loudspeaker, which is another transducer, which converts an electrical voltage signal into a sound, and that's what we hear. An amplifier, we hear an amplified sound. This is a very simple electronic system which uses just an amplifier and a combination of transducers. Okay. Now this amplifier need not be a single amplifier. It may be a chain of amplifiers, like the first one may be a simple voltage amplifier, and the next one may be providing voltage gain as well as current gain. It may act like a voltage amplifier as well as a current amplifier in general, followed by a current amplifier. So a question may arise regarding why it is so. The reason is the transducers you have are of different types. They have a different amplitude, they have different impedance levels. To match them and to see that the power gain is optimum from the input to the output, for the power gain to be optimum, we need to use different kinds of amplifiers. So please note that there are some voltage amplifiers, current amplifiers, and there are amplifiers which provide both current amplification as well as voltage amplification. Further, you please note that this particular amplifier may be a cascade of few amplifiers. This is a simple application where the processing of the signals involved is simple amplification. So at this point, let me explain to you that amplification is nothing but multiplication by some constant. Say this is one signal here, which is a time function, right? The amplified version of the signal looks like this. What is the difference between these two? it is just an amplified version of this. That means if its amplitude level is something over here, now its amplitude level is much higher than that, and the ratio between these amplitude levels is known as gain. If this is A and this is B, gain is defined as voltage gain, G is defined as B by A. It is as simple as that. So the shape remains the same, only there is amplitude is scaled. Let us consider another example. A gaseous analyzer, a gas analyzer to analyze gases. So that means from a given sample of gas, you should find out what is the chemical composition of the gas, what are the various constituents of the gas. So this kind of a device is very widely used in chemical laboratories and chemistry laboratories and laboratories of chemical engineering plants, and also in defense. You know that chemical weapons are a fairly recent development in the weaponry in defense systems. So the enemy is wiped out, contingents of enemies are wiped out by just releasing this kind of gases, nerve gases. Okay. Now as a defense measure, this kind of gas analyzers or gas detectors are used by the defense forces to sense whether the environment has any one of these nerve gases, toxic gases or not. Once these are present, some corrective measures like filters, using filters, so some corrective measures like using a mask to filter out these gases can be done, and the people can be saved. So in such gaseous analyzers, normally what we do is, typically what we do is as follows. Please look at this system. You use an IR source, infrared source, and so take the infrared radiation and subject the gas sample which is taken into a chamber. Naturally, you have to flush out the contents of the chamber earlier, evacuate the chamber and let the sample in. And then through a hole you let the radiation get in, and this radiation heats up the gas inside. Then use some microphone or some other transducer on the wall of the gaseous chamber so that the pressure variations can be tapped, and what you get here is an electrical signal. And this electrical signal needs to be amplified to bring it to a comfortable voltage level. Then it is analog to digital converted and fed into a computer for data analysis. This is one such typical system. To facilitate the amplification and processing of the signal, normally use a chopper. So you turn the chopper at certain speed. Then what the chopper does is, it allows infrared excitation of the gas on and off. Okay. That means the infrared goes into the chamber in pulses. So, when the infrared goes, depending on the kind of gas that is present inside, it absorbs the that particular infrared wavelength. Okay. So, this is the key point here in the detection of the gases. You normally excite a few wavelengths, and each wavelength, for each wavelength you measure the absorption. Okay. Say you excite a few wavelengths like 5 or 6 wavelengths, and for each wavelength you see how much is the absorption. How do you note the absorption? Depending on the absorption, the expansion of the gas takes place, and the expansion of the gases affect the transducer here like a microphone, and the amplitude of deviation it causes on the microphone diaphragm is proportional to the pressure inside, and pressure is proportional to the absorption of that particular wavelength. Therefore, the amplitude of the signal you get here at this point, you get a signal something like this. For on off you will get something like this, the signal would be something like this here. Whenever it is on, it gets excited, the amplitude is large, and whenever it is the chopper obstructs the light, so the light goes off and the absorption goes down. Therefore, you get some signal of this type at the output of the microphone, and the amplitude is directly proportional to the absorption. Now, after amplification, what we do here is convert this amplitude into a digital form. It is converted into an equivalent number, and that number is fed into a computer, right. Then for each one of these excitation, find the corresponding amplitude number. Now, once you have these corresponding numbers corresponding to these wavelengths, you look up, have a table lookup, and decide what kind of material is inside the gas. So, this is a typical gas analyzer. So, please note that some part of it is optical. This is the sensor part. It is optical and mechanical. It has optical parts as well as mechanical parts. The subsequent processing is completely electronic processing. So, you need electronic devices for this kind of operation. Similarly, you have gas chromatographs. Modern gas chromatographs use a lot of electronics in them. Let me give you another example. So, this time I will take up logic systems. So, these systems are based on some logic, not on amplification or things of that type. For instance, in a computer, how is the addition done, addition of numbers done? So, typically you use say for instance 3 plus 2 equal to 5, the arithmetic addition says that it is equal to 5. In a computer, typically we represent these numbers by its equivalent binary numbers, not decimal. The decimal numbers are represented in binary form because it is convenient to carry out these in electronic circuits. For example, 011 is the binary code for 3, 010 is the binary code for 2. When you add these, 1 plus 0 is 1 and carry is 0, 1 plus 1 is 2, that is 10, that means 0 is the result and carry is 1, and therefore 101 is the net result. So, let us see how this kind of addition can be carried out in an electronic circuit. This is a binary adder. So, I am adding 3 plus 3 and 2 and the result is 5. So, the binary equivalent of 3 is 0, 1, 1. I am representing this decimal number 3 in a 3-bit binary number, 3-digit or 3-bit binary number, that is 0, 1, 1. For 2 it is 0, 1, 0. When I add these two, 1 plus 0 gives me 1, carry is 0, 1 plus 1 is 2, that means the binary equivalent is 1, 0, okay. The result is 0 and carry is 1. When I add these 3, I will get a 1 and carry of 0. So, 1, 0, 1 is the result and its decimal equivalent is 5. So, this is how the binary, I have given here how binary numbers can be added, and equivalently the decimal number addition is equivalent to this. Now, the same thing can be done in electronic circuits. The circuits, electronic circuits can be made to understand say positive voltage, distinguish between say a positive voltage and negative voltage, or something like say some 3 volts or 0 volts. So, like this. So, it may not be able to distinguish various voltage levels, but logically, so it may be able to distinguish certain voltage levels like positive, negative, 5 volts, 0 volts, so like that of the type. Subsequently, you will see how this kind of binary addition can be done in an electronic circuits. We have circuits like logic gates which can do this job. We have an AND gate, for example. What the AND gate does is, it is a 2-input single output device, an AND gate. If you give 0, 0 as the input, the AND gate gives you a 0. At this input you apply a 0 level, some voltage corresponding to 0 level, and here also you apply 0 level, it will give you 0 level as the output. If you give 1 and a 0, it will give you a 0 as the output. If you give a 0 and 1 instead, also it will give you a 0 output. 1, 1, it gives you a 1 as the output. Okay. So, that means it acts like a multiplier. It is 2 binary bit multiplier. 1 into 1 is a 1 and 1 into 0 or 0 into 0 is a 0. So, what are these 1s and 0s? So, these are voltage signals. Okay. So, you may, for instance, you may designate a 0 by a 0 volt, approximately 0 volts, and you may designate 1 by an approximately 5 volt signal. So, that means when any one of them are around 0 volts, when any one of the inputs are at 0 volts, the output would be around 0 volts. If both of them are around 5 volts, the output would be 5 volts. So, you can make electronic circuits of this type using devices like transistors and resistances. It can also be built with diodes and resistances. And when you use several such gates, the combinations of such gates, you can make circuits which can do these additions and which can do multiplications. For instance, an arithmetic logic unit, ALU, arithmetic logic unit, ALU, is an integral part of a CPU. a central processing unit, which is the heart of a computer system. So you are hearing about Pentium systems. Earlier you heard about 486. So these are all CPUs, central processing units, which are the hearts of the computing systems. And the arithmetic logic unit is an integral part of a CPU. And what the arithmetic logic unit consists of is several such, there are things like the binary adders and multipliers, and some registers to store such numbers. And these are made with the help of several such gates. You have other gates like OR gate. The symbol for OR gate is like this. This one acts like a single binary bit adder. So when it is 0 0, output is a 0. When it is 1 0 or 0 1, output is a 1. When it is 1 1, output is again 1. So except for that carry, it acts almost like a binary adder. There is another gate known as a NOT gate. You give a 1 here, you get a 0 there. If you give a 0 here, you will get a 1 there. So it gives the opposite. So you can build logic systems using such gates. It is possible to implement this adder with the help of these OR gates and AND gates. Okay? So you will learn more about it in the subsequent classes. And other applications include vibration analyzers, robots. For example, robots are very widely used in manufacturing systems. So in painting a car, in assembling a car body, and similarly other systems. So what the robots do is they have an arm or one or more arms. So it picks up an object and does some mechanical job. In the process, please note that the arm works with different kinds of loads at different times. And when it picks up at different kinds of loads, to turn it in a particular angle, you need different amount of excitation. Okay? The system equivalent itself is the system becomes a nonlinear system, and to make the system work, carry out the same job with heavy load and with light load, with both, it should turn exactly the same angle and lift by the same amount of distance. Okay, lifting it by the same amount of distance are the kind of actions that are involved. So to carry out these actions, irrespective of the load, you need a lot of electronic support to the robots. In fact, you need computer control for the robots. Okay, so before that, you have to condition the signals by passing it through filters, amplifiers, and digital convert it, then control it through a computer, and from the output signals from the computer goes through another power amplifier, digital to again analog converter, and then back to the robot. Okay, so there are many such applications. I think I have discussed about a good number of applications, and I hope you have appreciated that the electronic circuits have applications in various fields of engineering and science, and important for all disciplines. Any questions at this stage? If there are no questions, let me introduce another important concept. Since we deal with signals and process signals in electronic circuits, let me introduce an important concept, so known as the frequency spectrum of signals, or frequency domain representation of signals. Usually, we represent the frequency domain representation as the spectrum of a given signal. As I explained here earlier, a signal can be a time function. Once it is electrical, it is either a voltage signal or a current signal of this type. When you look at it, what do you understand? You understand the shape of the signal, right? If it is a sine wave, you understand that it is a sine wave. If it is a square wave, you understand that it is a square wave. And very often signals have several components in it. So they look like they may look like noise to you. Okay, if you look at the time waveform. On the other hand, when you look at the spectrum, its spectrum means frequency versus amplitude plot. So like this, say this is 0.99 megahertz and say this is 1.01 megahertz. So this is the spectrum of the signal, and I'll explain what it means. And when you look at it, what do you understand? You understand that the signal is centered around 1 megahertz. It's a narrowband signal with the frequency components ranging from 990 kilohertz to 1010 kilohertz. That means bandwidth of the signal is 20 kilohertz. Okay, so this description is more interesting and more informative than this information than the time function itself. So very often the frequency domain representation gives you more information than the time domain description of the signal, particularly if it is a random signal. Now let us discuss about what is this frequency domain representation. Now this signal, if you decompose this signal into what are the various frequency components in the signal. What do you mean by frequency component? Do you have any signal with single frequency? That means a monochromatic signal. A sinusoid can be treated as a monochromatic signal. It has a single frequency, real frequency. Okay? So if you treat that as a monochromatic signal, and any signal of this type can be decomposed into several sine waves of different amplitudes and different frequencies. So that means this signal has several frequencies in it, several frequency components in it, and each frequency component may have some amplitude and some time shift as well. Now if you plot the same signal as a plot, amplitude versus frequency plot, that means for each frequency how much is the amplitude that is present in the signal, and that way it becomes the frequency spectrum of the signal. Naturally, when you have that kind of a signal, you will understand that there are no frequency components in this signal up to 990 kilohertz, and there are no components beyond 1010 kilohertz. All the frequency components are within this band, and they have amplitudes, various amplitudes levels like this. So this description is more informative than a direct signal. So, this is what is known as frequency domain representation of a signal. How do you do it? I am sure you have studied about Fourier series earlier in your +2 level. According to the Fourier theory of Fourier series, a periodic signal can be expressed as a constant plus a fundamental plus a second harmonic plus third harmonic and so on. A given signal can be decomposed into several cosinusoids and sinusoids. Let me add some phase term here. So, a given periodic signal can be represented as sum of several sinusoids with different amplitudes and different phase shifts. I will give you an example here. If you take for instance a square wave of this type, now I will try to represent this square wave as a sum of several sinusoids and sinusoids rather. So, you consider this sine wave. So, how is this sine wave? Is it almost same as this except for some error, some difference? Okay. How much is it different? At these edges there is a large difference, but in the center the difference is not much. So, can I use this as an approximation to this? A bad approximation, of course. I can use this as a bad approximation to this. Now, let me add another sinusoid to this. Okay. So, please note that the frequency of this sinusoid is same as the frequency, the fundamental frequency of the square wave. Now, I am adding a small third harmonic. This is a fundamental component of this square wave. Now, I am adding a small third harmonic to it because its frequency is 3 times the fundamental frequency of this. Now, if I sum these two signals, what is the net result? So, you will find that this is adding some voltage to this, and at this point it is subtracting some voltage because this is negative and this is positive, and at this point again this is positive and positive. When I add these two, it will further add up. So, the net result would be something like this, right? And if you look at the negative cycle, so here it will be like this. Is it more close to the square wave than this sine wave itself? It is very closely equal to this square wave. If I add another fifth component, fifth harmonic to it with an appropriate amplitude, I can show that this can be much more closer to this than this one. Like this, if you add different harmonics at appropriate amplitude levels, you can show that you can make up this square wave from these harmonics. Yes, asymptotically with infinite number of harmonics it will be exact. For all practical purposes, well, after maybe say 10th harmonic or 20th harmonic, you can neglect them. say this is to make up this signal, say this is a 1 volt peak signal, you may need say 1.2 volt peak, this is not exact, but I am giving as an example. You may need a 1.2 volt peak fundamental, right, and you may need say something like say 0.3 volt peak third harmonic, and say 0.1 volt peak or 0.2 volts peak fifth harmonic, and so on. Okay, when you add up all this, it will become this. Asymptotically, as you go, when you consider infinite number of components, the error almost tends to 0 in this particular case. Yeah, there is a doubt somewhere.
So, why are you always taking the odd harmonics?
In this particular case, depending on the shape of this signal, the symmetry of the signal is such that when you add the odd harmonics, it makes up. If you try to add the even harmonics and find out a solution, you will find that the even harmonic amplitude is 0. On the other hand, you take a ramp signal of this type. If you take a ramp signal of this type, it does not have this kind of symmetry, and you need all harmonics there, even fundamental, second harmonic, third harmonic, and so on. So if this signal is a sinusoid itself, if this signal is this sinusoid itself, how many harmonics does it have? Only one harmonic, so all other harmonics would be 0. So it naturally depends on the shape of the input signal, nature of the input signal. Okay. Now, therefore, according to Fourier series, you can represent a given periodic signal as a sum of several harmonics of the signal with different amplitudes and different phase shifts. And the same thing can be expressed as, if you remove the phase shifts there, it can be expressed as a sum of several cosinusoids and sinusoids. Okay? So there are different variations of the Fourier series, so that are present. Now, a spectrum is a plot which is the amplitude versus frequency. What is this component? This component has a frequency omega naught, and what is the amplitude of this component? A1 is the amplitude of this component. So this has a component, frequency component 2 omega naught, its amplitude is A2. It may have say 3 omega naught, amplitude is A3, and so on. And if you plot frequency versus amplitude, so at omega naught I have so much amplitude, at say 2 omega naught I have so much amplitude, at 3 omega naught I have so much amplitude. So this is amplitude versus frequency plot. In some signals which are non-periodic, so you will find that they have all frequency components. It is not that it has omega naught component, 2 omega naught component, and 3 omega component. It is not discrete frequencies, it has all frequencies. It is a continuous frequency band. So such signals have this kind of continuous spectrum. Okay, amplitude versus frequency plot is a continuous spectrum there. So you consider a speech signal or a picture signal or a geological signal like a seismic signal, a pH value. So if you consider a vibration signal, they have their spectrum. You can represent them in the frequency domain also, and as I said, the frequency domain gives you more information very often. Okay. Any questions? Questions? Hence, electronic circuits are applied in various fields of engineering and science, and I repeat, they constitute some building blocks like amplifiers, wave shapers, logic gates, flip-flops, and combinations of the above. And in this course, the basic electronics, we are going to study about all of these, I mean rather most of these. Okay. So, we will start with some electronic devices first and learn about a diode, first semiconductors, then followed by a diode, semiconductor diode, then its own applications, and a transistor, which is one of the greatest inventions of this century. A transistor will be studied. Then we will discuss about transistor amplifiers, and we use transistor as a switch, and we use the transistor for logic gates, logic gate implementations, and so on. Okay. So, now you know what the course content is going to deal about. Okay. So, from the next class onwards, I will discuss about the electronic materials and then circuits.